Hello, this is the next video in a playlist that I'm calling Hypothesis Testing. And within that playlist, we're in the unbiased test phase. And here we're going to look at a two-sided, uniformly most powerful unbiased test looking at the variance of a normal distribution. So I'd encourage you to watch the video that I have called Unbiased Hypothesis Test, where we look at the theorem of unbiased tests, and also we do an example about the mean of a normal distribution. So here we're going to example, we have our data xi distributed normally, mean 0, variance sigma squared. We have a sample size of n. We're going to do an alpha level test. The null hypothesis is that the variance is equal to some value, sigma naught squared, versus the alternative that sigma squared or the variance is not equal to that value. Now, a data point is distributed normally, and then this is the density of a normal distribution with mean 0. And it can be rewritten in this fashion where these constants out front we can just generically call tau. Then it's easy to show that the sum of the x squareds would be sufficient for sigma squared. I'm going to put a little subscript I there. And we also can show that y, the sum of the x's, divided by the known variance, the true variance, is distributed with a chi-squared with n degrees of freedom. Then, if we multiply the sigma squared up, y is distributed a constant times this chi-squared random variable with n degrees of freedom. Now note that minus 1 over 2 sigma squared is a one-to-one function of sigma squared. So that means we can back solve for sigma squared in using this relationship here, and then it turns out sigma squared is minus 1 over 2 tau. So it turns out that test for tau and sigma squared are 100% equivalent. And the UMP test is given by phi of this is a vector xi, so it's of our data x1 through xn. We reject if our test statistic y is less than some value called c1 or greater than some value c2, and we do not reject if it's between those two values. Now, why is there not a gamma 1 or gamma 2 in here for a randomized test? And the answer is, since our test statistic is continuous, then the probability that it equals a value is 0. So the gamma 1 and gamma 2 don't play a part in a test function or the rejection region when the test statistic is continuous. Now, here's a big note. If we divide everything by a constant, it actually doesn't change the probabilities associated with rejection or acceptance. So what we do, and this is a key point, we divide everything by the assumed true variance. So our hypothesis is this. So we're assuming the true variance is sigma naught squared or not. So under the null, we assume that it is. So we divide everything by that sigma naught squared. And so here we have y divided by sigma naught squared, and this is just another constant we'll call C1 prime. And then, but we do that because this is distributed with a chi-squared random variable, right? And now we can start calculating probabilities much easier. So we'll just call this W now, right? And so if we can solve for C1 prime, which is much easier than solving for this initially, then we can just multiply it times that C naught squared, and we get C1 back. Okay, so using this test function, where W is y over sigma naught squared, to solve for C1 and C2, we have these two constraints. It's the expected value of our test function, assuming that sigma naught squared is true, and that equals alpha. And the other constraint is that the product of W times our test function, the expected value of it, is equal to alpha times the expected value of our test function. Now, Here, this is pretty straightforward. It's the expected value of a discrete function. So it's 0 times the probability of it happening, 1 times the probability of it happening. So alpha, and then this expected value is this probability, right? It's 1 times these probabilities, where W is a chi-square random variable with n degrees of freedom. Okay, so that's the first constraint. The second constraint is, in this probability, I show what it is. It's, since we're a chi-square random variable, it's the integral from 0 to C1 prime of that chi-squared density, and this probability is from C2 prime to infinity, right? W greater than that, of that chi-squared random density with n degrees of freedom. Now the second constraint, this is easy. So right, it's alpha, and the expected value of a chi-squared random variable with n degrees of freedom is just n. So that's this one. Now here, it is the, we're either taking W times 0 or 1, depending upon where we are. And so the 0 doesn't play a part, so let's ignore it. Then it's W times the probability that we're in that region. So from 0 to C1 prime of that density, plus C2 prime to infinity, W times that density. So this is the other constraint. Now we have one equation, two equations. We're going to manipulate this a little bit. Actually, see this right here, W times a chi-square distribution. There's an identity that we're going to use, and so this is a side note. W times a chi-square density of n degrees of freedom is the 100% the same as n times a chi-square density with n plus 2 degrees of freedom. So wherever we were integrating this, which is in both integrals, we're going to substitute this. F is a chi-square density with n degrees of freedom, n plus 2. So we'll just substitute it here, and we'll factor out the n. We'll do the same to this integral. Now, so we have alpha n is equal to n times this plus n times this. So we divide everything by n, and we're left with this. And this is the second equation. So we have two equations, two unknowns, so we can solve them. And so, yeah, two equations, two unknowns, and we can solve it. It's actually so easy. It's one line of code in R, but I'm going to give you my thought process on how I got it down to one line of code. Otherwise, I couldn't make it a video. And we'll just use R to solve this. And it's so easy, so straightforward. Now, one interesting thing, solving this without a computer is so hard. You can't do it with, you can't really do it with a book or anything. It's too difficult. And the probability of the left tail and the probability of the right tail are not equal. They're not equal to alpha over 2, in this two-tailed test. But it is the uniformly most powerful unbiased test. But a very common approach, and probably the most common approach, is what's called the equal tails approach. So the probability that you're in the left tail is alpha over 2, the probability in the right tail is alpha over 2. So if we use the first constraint and then just make this probability alpha over 2 and this probability of alpha over 2, so that means set each of them to alpha over 2, then we can actually look in the back of a book to solve for these constants. And it's so straightforward. It's just the chi-square random variable with alpha over 2 area in the right tail. That's what C1 is. This is backwards. So this is the left tail. Oh, darn it. Right? Because this is the probability that we're less than some constant. So alpha over 2 is the area in the left tail. Now remember, we're solving for C1 prime. So to solve for C1, which is the original test function, we have to take it times the null hypothesis value. So sigma naught squared times that chi-squared variable. Now, to solve for C2, so this, we want the area in the right to be alpha over 2. So that means left of this value is 1 minus alpha over 2. That would be the C2 prime. And to solve for C2 in the original test function, we just multiply it times sigma naught squared. And this is a pretty good darn approximation to the unbiased test. So it's not unbiased, which means at some part in the alternative region, the power function dips below alpha. And in our video that we do next, we'll illustrate that. But the power functions are really close, and this is so much easier to solve for, and probably what most people use for this. Now, so in the next video, we're going to do an R illustration. We have n equal 55, alpha level of 0.05. We're going to do a test that sigma squared is 11 versus it's not 11. Our test statistic will be y equals the sum of the xi. And we will show that the test function is this. So this is C1 and C2 that we need to make this the uniformly most powerful unbiased test. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.